what you actually do to assemble a two-form, so a left-hand side, a matrix, is you take your integrand. So recall that our integrand looks like grad phi I dot grad phi j plus phi I phi j integrated over the domain. And I transform everything I can see, which is called pulling back. I pull back everything I can see into local coordinates. So the integral is pulled back to a local integral, and I multiply by the determinant of the Jacobian, just like we've done on 2 previous occasions. The mass part of the operator, so the part with no derivatives, is easy because, as previously mentioned, the value of the local basis functions is the same as the value of the global basis functions, so you just replace local by global. And now the gradient parts is just substituting what we just did. So you get a Jacobian hitting this guy and a Jacobian hitting this guy. When you do this, you have to keep very careful track of all the indices because you are taking minus jt onto this guy and minus j minus t on this guy and then dotting them together. It's quite easy to end up contracting the wrong thing against the wrong thing. So this is just a question of being mega pedantic, and you've all got maths degrees, so you understand the importance of doing the pedantry bit. And you might, depending on, and then what we do is we expand in quadrature points. So what does expanding quadrature points mean? It means what is said all along. So we multiply by the quadrature weights, and everywhere in here we see something which is a function of space. We replace it with that thing evaluated at the set of quadrature points. So this guy's evaluated at the quadrature points, this guy's evaluated at the quadrature points, this guy, and this guy. So now I've got an actual sum that I can do. And what this thing actually is a really big tensor contraction. And so you might find it easier, depending on where you went to university and which notation is your favorite, to write that in tensor notation instead. So you can either write out all the dots, or we can substitute in indices. So this is where it becomes relevant that we have this convention about which letters we use for which indices, because it makes this slightly less unintelligible, because there's a lot of indices on the go in this expression. So i's and j's are test function, trial function. Q is quadrature points, and now all these Greek letters are the geometric dimension. And so what's going on? So this guy is a, for each quadrature point, for each basis function, it's a vector in local space. Because we're multiplying by j minus t, that amounts to summing out over the first index, not the second index here. The same thing happens over here. So this guy is indexed by beta, and we multiply by that one here. And then that dot product becomes the sum out over the remaining index, which is sum out over alpha in here. So that thing is a number for each quadrature point. And the sum out over quadrature points happens here. And I do that for each I and j. So what this actually does, if I ignore what happens on the left-hand side, is this makes a local matrix, which is I by j. And I and j loop over the number of local basis functions. So if this were a two-dimensional piecewise linear element, I'd get a little 3x3 matrix, which is this integral evaluated for each pair of test and trial functions which are non-zero on this element. And that scales up. So if it were P3, it would be 10 by 10. And what do we then do with that? Well, those local IJ combinations correspond to global degrees of freedom. And so through the cell node map, you can expand those out and add them into the right places in the global matrix, for which there is a nice diagram here. So you have a local, for example, 3x3 system, and through the maps you know which global number this row corresponds to and the column. And actually, in this case, because we are only solving one PDE at a time, the test space and the trial space are always isomorphic to each other. And so it always works out that the global row corresponding to this one is actually the same as the global row corresponding to that one. So it explodes out into this nice pattern here. So now we get into a evil NumPy feature or misfeature, depending on which way you want to look at it, which is you might reasonably have assumed that if I have a set of global node numbers and a local matrix, I could do this. No. For reasons known only to the NumPy developers, if you index a NumPy array with two sets of values, you don't get the submatrix corresponding to all combinations of these two. You get the diagonal vector corresponding to these two. Who knows? So having at least partially conceded the heresy of what they have done, the NumPy developers provide a convenience function that does the right thing. So this convenience function, which is inexplicably called ix underscore, does that explosion for you. So if you index A with ix nodes, it really does refer to the set of all i's and j's from that set in the right order, such that you can add something onto the right-hand side. Sometimes other people's design decisions are inexplicable. It's not a problem on the left-hand side, right? On the left-hand side, if you've got a set of nodes and a local vector, sorry, it's not a problem on the right-hand side. If you've got a local vector and a set of nodes, then that one works. That's fine. It's only a problem once you have more than one set.